Yes. Google Hangouts, Google.
No, sir.
Okay, okay. So you can send me schedule at even email. We can talk together, no problem. Or from my mom's WhatsApp. Okay.
Okay,
Is
sure.
my screen shared with you?
Yes.
Okay. Bismillah. Right. So here, this would be of your 45 minutes paper, right? It is 2019 paper 3 HL. Okay, ji?
Yeah.
Morning time. And it would have your questions with option, and you are taking astronomy, right? It
Yeah.
is over here. Question 15 and 17 are there for you.
Okay.
So let's go to that. Question 15 and 17. Wait. Yes. 1 and 2, we have to answer all of these questions. Yes. So
Okay.
a student investigates how the time period of a simple pendulum varies with the maximum velocity or speed v of the pendulum's bob by releasing the pendulum from the rest from different initial angles, right? It is
Yeah.
basically the relationship between time period and angle. The graph of the variation of time period with speed is plotted in the table. Okay, speed is given to you and so on. Suggest why the reference to the graph, why it is unlikely that the relationship between t and v is linear. Yes. So from this graph, w- how we can predict that this relationship is linear? If I
It's
draw a best fit,
it's an
right?
exponential. It's exponential increase.
Yeah, so it is not actually going to meet the straight line, so it is incorrect. It means that's why it is not linear. And for linear there is another um, situation that all of these points are passing through origin, or you can say that the line is passing through origin. So that is why you can say that graph is not linear, so it is not a straight line. Okay,
Yeah.
not a straight line of best fit. And secondly, straight line of best fit, because that is 1 mark, and also not passing through origin. If I draw a straight line, it will not pass through origin. Or simply you can say, no need to write it down. That's it, simple, that it is not the straight line of best fit. Now, given the fractional uncertainty in V, where t is 2.115 seconds, correct to one significant figure. Okay, so we have to find the uncertainty in V at time is equals to 2.115. So where is time is equals to 115, 2.115. So I have to find out where is 2.115. It is 2.11, and probably this is 2.115 option. Is it?
Yeah. Yeah.
So, so fractional uncertainty means, the game of error bars. How much uncertainty do we have? This is basically this point, and secondly, we have to consider that this is what is the height of this error bar.
0.05.
Yes, 0.05. So if I say it is 0.05 uh, seconds, because 1 2 3 4 5 squares are there, and 5 squares are equals to 0.01 0.01, na? Is it?
I thought it was 0.05, no?
No. From this point to this point. I'm saying from this point to this point. Is it?
Oh, yeah, 0.01. Yeah.
Okay. So this is what this one is of 2 squares. This is equals to 2 square. So we can say that if 5 squares are equals to 0.01, then 2 squares are equals to 0.01 times 2 divided by 5. Isn't it?
Yeah.
So it is 0.02. Sorry, 0.0. Wait. Let me calculate that.
0.04.
0.44, because this is your 0. Uh, 0. Okay, so one small square will be equal to how much? Let me calculate one small square equals to 0.01, 0.012. Yes. So 5 is equals to this. So one small square equals to 0.01 divided by 5. So what will be that? Do you have calculator?
Yeah.
Oh, yes. So what will be that one?
2 times 10 to the power of negative 3.
Okay.
So 0
0.
0.002.
2. Yes, exactly. So it means how many of these two? These two are equals to, it means two squares are equals to 0.004, isn't it?
Yeah.
So it is 0.004 is the uh, fractional, sorry, is the absolute uncertainty over here. I mean, the deviation. So this deviation is basically from upper bound to the lower bound. So we have to take the uncertainty from this point to this point. So actually, over absolute uncertainty over here, delta t is equals to 0.04 divided by 2. I actually, why did I calculate this all? Because I wanted to tell you that basically this is the standard deviation, or the deviation from lower bound to the upper bound. So when we calculate that all, sorry, when we calculate delta absolute uncertainty, either absolute uncertainty is from your mean value to the maximum. Absolute uncertainty has this concept: f of x maximum minus f of x, or f of x minus f of x minimum. I mean to say, maybe I'm using difficult words for you. This is your x. This is your x max. Okay. And this is your x minimum. So if you want to calculate uncertainty, what you got it over here, what error bars tell you, error bar tells you this is your x minimum and this is your x maximum. Are you getting it? Are you aware of this concept?
Yes.
Okay, so actually over delta x is either between these two or between these two. Got it? So simply speaking, x max minus x minimum divided by 2, that is your delta x in this case of uncertainty. Remember this concept. So we got that. So it is delta t is equals to 0.002, and t is, oh, what is t over there? He has given time 2.115, right? So are you aware how to calculate fractional uncertainty?
Uh, isn't it 2.115 divided by 2.115? Sorry, 2
Uh,
point T
no,
delta T upon
ulta.
T.
Yes, delta t upon t, okay, which is equals to 0.002 divided by 2.115. So just calculate this one.
9.45. Wait, sorry. 2 over, sorry. I'll give the fraction.
It,
Uh,
yeah, it would be very small number.
yeah. 2 upon 2.115.
So just convert it into decimal.
9.46. Wait, how many this? Oh, 3. So 9.46 times 10 to the power negative 4.
-4. Okay. So if I write, because he has stated to one significant figure. So one significant figure mean, if I write it 9.4, it is basically 10 into 10 raised power minus 4. And now this is the two significant figures. If we consider the number of digits before decimal, sorry, before multiplication, there are two. So there are two significant figures. So I can write 1 into 10 raised power minus 5 seconds. Got it?
Okay.
Or in
Yeah.
other words, you can write 0.00001. Yes. Got it?
Okay.
Or if you want
Yeah.
to round it off to this number, it can be written over here. Or there are so many ways from this. So if I write it is 0.946 into 10 raised power minus 5, then I can round it off to 0.9 uh, times 10 power minus 5, which can be 0.00009. Is it 0.0009
Yeah.
in, yeah, that's it. So you can write in this way. Is it clear?
Yes, sir.
Okay, good, very good. Now come to this part. This question is continue. The student hypothesis that the relationship between T and V is T equals A B squared, where A is the A and B are the constants. To verify this hypothesis, the graph is showing the variation of T versus V square. The graph shows the data and the line of best fit. Okay, the graph shows the data of line of best fit. And okay, very important thing, if you are going to take the graph of V square versus T, then it would be straight line passing through origin, or not passing through origin even, but it would be a straight line, because we when we were talking about the previous graph, it was the graph of T versus V. So they are not having linear relation. But if we take V square, it would become linear. Yes, this is a straight line passing through origin. What he wants from us, determine V giving an appropriate unit for B. So what we have to do, we have to determine B, and we have to give a proper unit for that one. So if I want to mean these type of questions are actually solved in this way, that you have to make all the equations in the form of y equals mx plus c, right? How
True.
do we make these equations? Yes.
Oh, so we can go equals to T equals to A plus B V square.
Yes. Yeah. So equation was T equals, what was the real equation over here? T is equals to A BV square. So T is equals to A plus BV square. So if I say that this is my Y is equals to BV square plus A. So can I say that my gradient from here, or M, is equals to uh, B, my y intercept is A. Am I right?
Yeah.
So when I have figured it out that my gradient is B, then I will find that yes, value of B from here by finding the gradient. So gradient
Rise
can
over
be,
run.
yes, rise over run, or you can say y2 minus y1. So you can plot 2 points which are exactly on the line. This is very important over here. Let me show you the points first. For example, if I set, we set the points which are exactly passing a corner, like this is a corner point, then I have to find out a corner point on the line, like this is a corner point. Okay, are you getting the
Yeah.
corner point? Check this one out.
Yeah.
Exactly where 2 points, squares are being intersecting each other. So I will draw a straight line over here, right? You can draw dotted line, because I don't have that tool with me, dotted line wala. So I can draw a straight line over here. This is how. Now if we take the gradient, what are these 2 points here? This is your 0.5. So I can say that this has coordinate 0.5, and what will be that one? 0.1 0.12
4. 1 4.
0.14. Yes,
1
2.14.
4.
Oh, no, oh my god, 2.14, not 2.14. It is 2.10, 2
4.
point,
104?
2.1 was, yeah, 2.104, 2.10, yeah, 2.104. It would be 2.104. Okay. And what about the top point? It will be
It
4
will
point
be 4,
1,
4
2, 3, 4, 5, 6, 7, 8, 9, 10. It is 4.1, 4.2, 4.3. Isn't it 4.3? Is it?
yeah,
It is
4.3.
4.3 over here. So it is your 4.3, and your y-axis is this, and from here it is 2.150,
152.
152. Sorry, 2.152. Very good. So just find the gradient over here. So if I find the gradient, so b is equals to y2 minus y1. It means, let's write formula first: y2 divided by 1 divided by x2 minus x1. Then after that, we can say that y2 is 2.152 minus 2.104 divided by x2 is 4.3 minus 0.5. Okay,
Yeah.
because we have to write down the unit as well. There is no, remember one thing, this is the important thing. If you have any exponent, for example, if it is written in this way, v square slash 10 power 3, so you have to consider that as well. Okay, but that is not here. That's why it's not a big issue,
Okay.
right?
So, yeah.
Yeah. Can you please calculate this for me?
0.01.
0.01. That is your gradient. But what we have to write, we have to write the unit of that as also. So if we are going to write down its unit is, because b is equals to the y-axis, are the top is t and the lower one is v square. So it is t divided by v square actually, which is second divided by meter second minus 2. So it can be further written as meter minus 2 second minus 3. Are
Yeah.
you getting it?
Yeah.
So you will write that unit is equals to m minus 2 s minus 3. Is this clear?
Yeah. Okay.
Okay, good. Fine. Now come to this question. Please do not write on this page answer written on this page. Yeah, I get it. The line of the minimum and maximum gradients are shown in the figure. The line of minimum gradient and maximum gradient means these are two lines. One line is called your line of best fit. The second line is called your line of worst acceptable line, right? So uh, here we use the term lines of two gradients. I mean, these two gradients are maximum and minimum. So which line would have maximum gradient? Your this line would have line of gradient maximum, and this would have your gradient of, this will have your minimum gradient, isn't it?
Yeah.
Okay. Now, what is the instruction? Estimate the absolute uncertainty in A. Wow. Absolute uncertainty in your A. So, what was A, by the way? A was the y intercept. Is it? Check this one out. We have considered that A is y intercept. Okay.
Yeah.
So, what we have to do, uh, we have to calculate absolute uncertainty in the y intercept. So, for that purpose, we have to find out the two intercepts, and then we will basically subtract them, right? Absolute uncertainty in the y intercept is, absolute uncertainty in y intercept is equals to y intercept of maximum gradient. Okay, y-intercept of maximum gradient minus y-intercept of minimum gradient. And if you calculate that, that y absolute uncertainty in the y-intercept is equals to, what is the value of this line? It is 2.09, 2.092, 2.094, and almost 2.095. Is it?
Yeah, almost. Yeah, I could see.
Yeah, because it is estimate. So 2.095. And what about the top one? It is almost 2.101. Is it not? Because it is almost at the midpoint, this variation.
Yeah.
So if I want to calculate the absolute uncertainty over here, that will be 2.101 minus, which one has a maximum gradient? So you can say 2 point, sorry, 2.095 minus 2.101, or other way around. You can write either 2.101 minus 2.101 minus 2.095. Both are correct, no issue. Okay.
Okay.
Yes. So what will be your answer?
Uh, 0.006.
0.006. Yes, that is the absolute uncertainty. So if we want to find out the fractional and so on, we will proceed from here, right? Is it clear till now?
Yes.
Yeah, this was your question number one, and that was of how much marks? It was 2, 5, 7, 8,
Mm,
and yes, 8 marks, no?
yeah.
Okay, good. We have tried all those marks over here. So here is your question number two. Question number two is related to your circuits, right? A resistance R of a wire of length L can be measured by using a circuit as shown in the figure. So here, in one experiment, the wire has a uniform diameter of D 0.50 millimeter. The graph shows the data obtained from the variation of resistance with length. Actually, this is a sort of potentiometer type graph, you know. Potentiometer, you know potentiometer?
Yes, sir.
A wire connected with an emitter and a circuit, and we basically use it for a balanced condition, that where it would be balanced with another resistor, right? So this is actually that type of question. So whenever a topic or a question is there, just recall the topic of related to that question. Then you will be very clear about that. In an Okay, this is the resistance and length variation. We have all these points without absolute uncertainties. The line of best fit, almost it is passing through all the points. The gradient of the line of best fit is 3.6.30 ohm meter. 6.30 ohm meter.
Um,
Estimate the resistivity of the material of the wire. Give your answer to an appropriate number of significant figures. So whenever this word is asked, appropriate number of significant figure, it means that we have to think the least significant figure in our data. So the least significant figure in our data is here it is 3
one
significant,
sig,
here it is here
one
it is
sig
3
fig.
significant. Sorry.
And is it on the table one sig fig?
In the graph,
Yeah.
yeah, in the graph it is one significant. Yes, in the graph it is one significant. The values, right? He's saying that the gradient is this one. Okay, so what we have to find out the resistivity. So wow, what a question. Check the graph over there. If you know the equation of the concept of gradient resistivity, you know what is the or what are the factors upon which the resistance of a wire depends. Resistance is equals to resistivity L divided by area of cross section. Okay.
Yeah.
Okay, so we have to figure it out whether we are given with diameter or we are given with area. If we are given with diameter, so we will convert this equation back to R is equals to rho L divided by, what is the diameter of a wire? Sorry, area of a wire. If its diameter is D, its diameter is D, so its area will be equals to pi D square divided by 4. Abdullah, why did I do that?
Because that's the area of a cylinder.
Yes, exactly. So area is equals to pi r square, which is pi r is your d by 2 whole square. So it would be d square divided by pi square divided by 4. So I wrote this in this way. Now, uh, yeah, now I can rearrange my formula that resistance is equals to 4 rho L divided by pi d square. From here, I can say that I have to figure out the resistivity. So when I make resistivity a subject, resistivity is actually resistivity is actually okay. What is your format? You write horizontally or vertically?
Vertically.
Vertically, na? Just draw the lines. So because when we are going to have some calculations, we have to show step by step vertically. So that's why I am in the habit of drawing the lines and then complete the steps and moving towards right. Okay. So if you have your convenience, you can follow your own. No, I will not overlay my strategies on yours. You okay. So resistivity is uh, 4.
Or
Sorry, sorry,
point
sorry, sorry,
four.
sorry.
Pi
Pi
d
d
squared
square
r divided
r
by
divided
4L.
by 4L. Yes, now I got the exact track because R over L is my gradient, isn't it? Check the graph.
Yeah.
R over L, R upon L is my gradient. So I can rearrange this equation that resistivity is equals to pi d square divided by 4 times gradient of the graph. Okay, so we are having all the stuff over here. So resistivity will be equals to pi. What is the value of diameter? Diameter is your
25.
5.00 millimeter. We have to convert that into 5 into 10 raised power minus, okay, sorry, 5.00. 5.00 into 10 raised power minus 3 whole square, because it is d square and I have converted into millimeter, divided by 4 times what is the gradient? It is 6.30. Yes. Can you please solve that?
Yeah. 1.24 times 10 to the power
One-
minus 4.
1.24
24
into 10
power minus 4.
ohm meter. Its unit will
Meters.
be ohm meter, not ohm per meter, because resistivity is resistance of a wire per resistance of a wire per unit length, or resistance of 1 meter of a wire. You know?
Yeah.
Okay. So if we consider the number of significant figures in the raw data given, we have three significant figures overall. Okay.
Yeah.
So I believe that we have to write the number in this way. Otherwise, if we write in one significant figure, it can be 1 into 10 raised power minus 4 ohm meter, but it would have a lot of deviation. So this would be the appropriate value, right? Rho 1.24 exponent minus 4 ohm meter. Okay.
Okay.
Okay, good. Next is explain why the reference of the power dissipated in the wire. The the fixed resistor, advantage of the fixed resistor connected in
Yeah.
series with the wire for measuring of our wow. So what's your idea? Why do we use this one?
Yeah.
It is a
Uh,
safety resistor. Okay, yes, carry on.
Sorry, can you repeat this question? So it's you're lagging there for a
Yeah,
second.
the question is, we have, oh my god, I have to connect you. Did you ever have, did it ever happen to you that you have put the mobile at charging and you did not switch the circuit on?
Yeah.
Yes,
Yeah.
that same thing happened with me. I put my Evo, that charging device at charging, and I did not switch it
Yeah.
on. I was thinking that my network is that one. That's why it was lagging. Oh my god, sorry, man. Was it lagging for a long
Oh.
time or?
No, yeah, I was just lagging for just 1 second. But now it's fine. I think my Wi-Fi is also pretty bad. I don't, for some reason.
No problem. Just mean, MBBS.
MBBS, yeah.
No, no, not MBBS. Mbps.
Sorry.
Megabytes per second.
Oh,
Speed.
MBS. Yes. Oh, yes. Yeah.
MBs.
Yes.
Actually, it is MB MB
Yeah.
megabytes per second. What is that Mbps over there? Or MBs over there with you? Net speed?
Uh, Around like 40 MBS.
Oh, good.
I can't
That's
remember.
okay. No problem. Because I used to check it because here there is a lot of fluctuation. So I usually go to 30 Mbps, not more than that. This is the highest over here with me. So that's why it can fluctuate. I mean, I also find, fluctuations on my end. Okay, now
Yeah.
come back to the data. He is saying that it was your brake actually. There is a wire, and in that wire there is a resistor. This is your safety resistor. Okay, protection resistor. So protection resistor. So if I say that why it is being used over there with the concept of power dissipation, we have to consider this one, the concept of explained by the reference of power dissipation in the wire, the advantage of the fixed resistor connected in the series with the wire. So what is the function of this series resistor over here?
The
Yes, come on. Series
uh,
resistors.
Generally just keep the
Mhm.
resistors in line.
Okay, actually it enhances the resistance of the circuit. Okay, it increases the resistance of the circuit, and due to that the current in the wire will be limited. Now is it clear?
Yeah.
due to which current will be limited.
Okay.
Current will be limited. Current will be limited, and as current is limited, so heating effect of current are also decreased. Heating effects of current are decreased. So when you have decreased the heating effects of current, then what else you did? You have saved the power dissipation. So the power dissipation, as power dissipation is equals to, we have to put the reference because it is of 3 marks. As power dissipation is I square r, so it will be, it will also be decreased. It will also be decreased. Now, are you clear?
Yes.
Because simply I can tell you that when R will be increased, I will be decreased, and as P is equals to I square and R. Remember this thing. Because you can claim that, okay, sir, R is increasing, I is decreasing, then what's the effect? But I is decreasing by a square factor, and R is increasing linearly. So overall, what whose impact would be more? The square of I will be there. So overall power would be decrease. Got
Yeah.
it? Our energy loss would be decreased. In another way, you can say that energy loss decreases. Energy loss decreases. Okay. Now, is it clear now? Should I move to next question? The experiment is
Yeah.
repeated using a wire made of the same material but of the larger diameter. And the wire in part A, material is same, I mean resistivity is same, but diameter is more. On the axis in part A, draw a graph for the second wire. So for that purpose, what I have to work, that resistance is equals to resistivity, 4 rho L divided by pi d square, isn't it? That was the formula for resistance.
Yeah.
So I can say that as the resistivity is same, so I would make the gradient separate. R by L will be equals to rho 4 rho divided by pi d square. Abdullah, are you getting my points? Mean, if I'm not going fast, is it clear to you? By
Yeah.
all
It's
means,
clear. It's clear. Yeah. I understand.
very good, well done. This is the gradient. So check, the gradient is equal to 4 rho divided by pi d square. So very obvious that if I check the gradient, so gradient is inversely proportional to square of diameter. So as diameter increases, what he's saying, larger diameter. So as diameter increases, what will happen to the gradient? Gradient will be
Decreases.
decrease. Okay, so gradient will be decrease. So I can say that gradient is, it would not be linear. Sorry, wait. Because this graph is the gradient of R and L, so it would not have the relationship with square of this one, because that is, if the graph would be the graph of resistance and diameter, then it would be straight. But simply here we will say that gradient will decrease. So I will draw a straight line here in part A with decreased gradient. So you can say that any, but there would be a limit for that. For example, I have to start and stop the points from the same situation this way. You can say, for example, it is not written that diameter is doubled. If diameter would be doubled, then gradient would be definitely 1 by 4. So I have to set the points. For example, one. I have to set the points 4 times lower. 4 times lower. How means? How? It is 1, 2, 3, 4, 4.5. Na. So that would be 4.5 divided by 4. So it would be at 1.1 almost. So 1.1. It should be, the gradient should be anywhere here.
Yeah.
Okay, but it is not written that diameter is half or something. It is just written that diameter is large. So when diameter would be increased, gradient would be decreased. So this is the new line. Okay, new line with larger diameter. Okay, ji. Should we move to the next? Oh, we are not still at, we are at 8 pages, but there are 33 pages actually.
Yeah, but
Okay,
most of
this is
those
now
33
section.
pages are the other ones.
Yeah, the other ones. Now we have to reach to our questions. You are taking astronomy, na?
Yeah, yeah.
So I think the astronomy was declared in question number. I checked that one out, but 15 and 17. I mean 15, 16, and 17. There are three questions at the last, so let's move to those questions. 15 and 17. Come on. Yes. 15, 16, and 17. Okay. Okay. Oh, there are so hard names. I really hate these names. Eta Cassiopeia A and B is a binary star system located in a constellation Cas, what is this here? Cassiopeia, whatever that is. You can pronounce it
Mm,
for you. Okay. Distinguish between the
yeah,
constellation and the stellar cluster. So
yeah.
constellation is basically the
Stars.
formation of, yes.
A constellation is just a group of stars that is recognized by an obvious pattern.
Sorry, can you repeat? The constellation is
Group
the
of
combination of
stars that is
stars.
combination of stars that is recognized by a pattern.
Yes, that is recognized by patterns. And cluster is just a word that, yeah, there is a cluster of stars. So cluster is, and any non-patternized, or what can I use a proper word for that? Random patterns, isn't it?
Yeah.
Random arrangement of stars. Okay. Then after that we have the following data are available. The, what is it? Apparent brightness of the mm, eta Cassiopeia A is this one, and apparent brightness of V is this one. The luminosity is this one. Okay, the peak wavelength of the radiation from Eta Cassiopeia A is 490 millimeters. Show that the surface temperature of the Eta Cassiopeia A is about 6,000 Kelvin. So here I would need some sort of booklet information, because this is, uh, we can consider this with Stephen Boltzmann law, that is, do we have some other information till here? No, it was that temperature is inversely proportional to lambda max, right? And that was equals to the temperature times lambda max, that was equals to sigma, Ven's displacement law, sorry,
Yeah.
Ven's displacement law. So can you please give me the value of this Ven's displacement law from your uh, data booklet?
I'm just pulling it up right now.
Okay.
Second.
Yeah, is it
Uh,
printed with you?
I have a soft copy. Every time I had a
Okay,
printed one,
okay,
it gets destroyed. I just stick to
okay,
soft
okay, okay.
copy.
No problem, don't worry. Let me open it up. Maybe I will be able to open it up more quickly.
What's the displacement?
It is
Which value is that?
2.9.
The
Yes.
sigma, right?
Yeah,
Uh,
2.9 exponent minus 3. Is it?
Wait 1 second. It's
Yes.
scrolling. Sigma.
Temperature is to be remembered.
Yeah,
I mean,
five
we have to
points.
calculate.
Sigma is 5.67 times 10 to the power of minus 8.
No, 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 no. That is something else. That is your Ven's displacement law, the constant of Ven's displacement law. That
Constant.
other one would be the sorry, that sigma would be, okay, leave it. That
Stefan,
sigma
this one
would
is
be
a
the
Stefan
Stephen.
Boltzmann.
Yeah, yeah, that is just a constant number, and that is time is lambda max is what is lambda max? 490 nanometer. Is it
Mhm.
490 into 10 raised power minus 9, and that constant is 2.9 exponent minus 3. So can you please calculate that one? The temperature is equals to 2.9. You can directly put this value, no issue, divided by 490 into 10 raised power minus 9. So what will be your answer? It should be
Oh wow.
about
It's like how should I say it? How many sig figs? Two sig figs? So 5.9 times 10 to the power of 10 to the power of 5.
5. Okay, it would be 5. Just let me calculate as well. It would be 2.9 divided by. We should be able to grasp the answer like this.
Oh wait, 1 second. I made a mistake. Sorry. 5.9 times 10 to the power of 3.
3, yes. So it is almost 6,000 Kelvin. Yes.
Yes.
Right? Is it clear?
Yeah.
Okay. So, Yani, what you have to remember from this question, that whenever the peak wavelength is given to you, because there is another information, this information that is not required over here. Here, the peak wavelength is required over here. So the peak wavelength is given over here, this one. So this is your lambda max. So whenever this type of question is asked to you, you have to be very careful that we have to use Benz displacement law, not the Boltzmann law.
Yeah. Oh,
Boltzmann
sorry,
law
this
will be applied
question.
over here.
This ratio questions, I always have trouble with understanding the ratio questions.
Okay, okay, let me make you clear in this part. This, the surface temperature of the eta Capes,
Ethiopia.
Cassiopeia, yes, B is this one. Determine the ratio of radius of A and radius of B. So you know, here we have to follow that Stephen Boltzmann law. What was that? He
Different.
stated
Oh,
that the, yes, the square of temperature, sorry, luminosity is directly proportional to the square of radius or surface area of the star, or you can say, yes, it was in this way, the square of radius or diameter and temperature power 4. Did you remember this equation? It was something
yeah.
like this: 4 pi r square t power 4 with sigma over here. This was carrying a sigma over here, right? So simply luminosity is equals to 4 pi sigma r square t power 4. This was the question. I mean, this was the formula. So if we use that formula, what do we do? This is probably given in your booklet. I mean, that's formula formula booklet. Okay, now check this one out. What do we have? We have luminosity. We have temperatures. Do we? Yeah. Luminosity, apparent brightness is this one, right? And its apparent brightness, I mean, its luminosity, what we have over here, it is given in this question. And then we have their temperatures, right? What do we have? We have their temperature. So I can say that we can make a formula like this, that their apparent luminosity L1 divided by L2 is equals to 4 pi sigma R1 square T1 की power 4 divided by 4 pi sigma R2 square T2 की power 4. So if I cancel this out, I will make a relation L1 divided by L2 is equals to, actually this is, I believe that this is, oh, this is radiant flux intensity. Oh my god. This is radiant flux intensity. Check the data booklet. Maybe we represent it with L, because the solar luminosity is given to us. L naught is given to us, right?
Yeah. Uh,
That is F, I think. Sometimes
L
naught.
equals to
Uh-huh.
L equals to that equals to Stefan Boltzmann constant times area times T to the
Hmm.
power 4.
Okay, L. Okay. Sometimes I do not remember all these mess up of equations. They just jumble up in my brain. Okay, so sorry for that. L1 divided by L2, 4 pi sigma, that would be cancelled, and you will be left with R1 divided by R2 whole square, and then you are left with T1 divided by T2 whole power 4. Now, first make the ratio. Are you clear? How did I make this?
Yes.
Good. Now, after this, what is my uh, subject? My subject is this one. So I will make this number a subject. So I will say that L1 divided by L2 will be equals to T2 divided by T1 whole power 4 will be equals to R1 divided by R2 whole square. Are you getting it?
Yeah.
Okay, so now you can just make it A's and B's. So RA, and here it is RB. So one is your A and two is your B. So you will write this B, this will be A. You will write this one A and this two will be B. Now is it clear that how did I set the ratio?
Yeah.
Okay. Now just feel free. Just make this RA divided by RB a subject, because I have uh, taken square root, or if you don't take square root at the final answer, you can take square root. LA divided by LB into TB divided by TA whole power 4. Just do that. Put the values. Now are you clear that how did I make the ratio and how to use that?
Yeah. Yeah, I
if
understand.
you if you remember this formula, na, no need to write this all. You can start right from here, that L1 divided by L2 is equals to R and L are directly proportional to R1 divided by R2 whole square, and temperature is also directly proportional to that. So we can write T1 divided by T2 whole power 4, because its power 4 is over there. So just put the values of, I can write this over here. L1 is luminosity, apparent brightness of that is apparent brightness of A is 1.1,
Um,
because I have to use the data. 1.1 into 10 raised power minus 9 divided by, what is for B? For B it is
point
5.4 into 10 raised power minus 11. It is times, what is the temperature over there? Uh, For A, we calculated the temperature 600 Kelvin. For B, we have given 4100 Kelvin, right? So for B, we will write at the top 4100 divided by, for A, we will write 6000 whole power 4. Just solve this for me, and then finally we will take square root of that.
12.7. So 13. Basic.
12 point.
Actually, one sig. So 12.7.
Okay, no need to write insignificant figures right now. Whatever. What is your answer?
12.7.
Okay, good. Now take square root of that, because we need, what do we need? We need radius. I mean, the ratio of radius, not radius square. So this was the radius square. So you can say RA divided by RB is equals to 12.7
Oh, wait, one
square
second,
root.
sir. I missed out the one calculation. It should be 4.065.
4 point.
065.
Okay, 4.065. Then take its square root. 4.065. Yes.
2.016.
Uh, 2 point
016.
2.016. So it is almost 2.0. Okay. Radius of A divided by radius of B is almost equal to that. So did you make
Yeah.
some sort of rounding off as well? Oh yes, there is one issue. Oh my god. Listen. This was an approximation. Whenever the data is used after calculation, we use the true value what we have found. So it was 5.9 into 10 raised power. What was that? It was 10 raised power 3.
Yeah.
Okay. So 5.9 exponent 10 power 3. Just calculate from that one. जी अस्सलाम वालेकुम जी बल शुक्र अल्लाह ना अच्छा अच्छा ठीक है टाइम देखिए ना तो
So
कितना खा
4.35, and then square root of that is 2.085.
2.08 जी 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 हाँ तो तू सच्ची पहुंच लिया तकरीबन बताए 12 तक तो नहीं पहुंच सकते हैं 1 1:30 बजे तक पहुंच लिया होता है चलो अच्छा ना फिर देखने हैं यस यस अब्दुल्ला
2.085. 2.085.
2.08 ना so 2.085 mean it is almost 2.1 okay you got
Okay.
it
Yes, sir.
yeah that was actually if you have any confusion in the calculation still you can ask me
Sure, sir.
okay now is it fine calculations are fine for you
Yeah.
you can go through that all calculation once again I will make you a revision over here the actually what did we have we were given with some sort of data that was that temperature is given temperature of A was given to you temperature of B was given to you right temperature of A was 5.9 exponent what was the actual value of that actually we have to write it down anywhere where we are going to calculate so then we can use 5.9 into 10 raised power 3 was this one and it was 4.1 into 10 raised power 3 was that one and then we had apparent luminosity of A that was 1.1 into 10 raised power minus 9 watt per square meter was it
Yeah.
1.1 and the for the second one it was 5.4 for the second one lb was equal to 5.4 into 10 raised power minus 11 watt per square meter so what was required r1 divided by r, sorry, r a divided by r b was required, right? Is it clear? So actually in
Yeah.
that space I was having some limited option. That's why. Now here I know that temperature and this uh, luminosity is equals to 4 pi sigma r square t power 4. So from here I can make a relation of this length and all that stuff. Or if you want to make r subject, r will be equals to, yeah, r square will be equals to l divided by 4 pi sigma t power 4. Is it clear to you? So you can simply write that r1, sorry, ra divided by rb. This is another method. That's why I was resolving for you. La divided by lb, because that is directly proportional. R and L are directly proportional. Okay, and temperature 4 is inversely proportional to that. So temperature power, temperature of b divided by temperature of a, that whole power 3, oh sorry, whole power 4. Is it clear? So we calculated that all. This was having a square on it. So this all was solved by you and you solved it. It was 2.08, no no no, sorry, what did you solve for that one without square? 4.3 almost, right? So your ra divided by rb whole square was equals to 4.3. Okay, and just take square root of that and you would have the answer 2.1, which is basically equals to ra divided by rb. Now do you have any confusion in that? Is it clear to you?
Yeah.
Confirm na?
Yes, sir.
Very good. Okay, move to the next one. It is a distance of Eta Cassiopeia system from Earth is 1.8 exponent 17 meter. Oh, this is the distance. Calculate the luminosity L naught of in terms of L naught of the luminosity of Cassiopeia. Okay, so for that purpose, what do we have or what information do we have? We know that luminosity is basically, uh, you know, the luminosity can be written in terms of L naught. Okay, and that luminosity is related with the formula of, or simply you can say that luminosity is directly proportional to that value of what is that 4 pi r square, right? And
Yeah.
then the Boltzmann constant, right? So I can say that it is 4 pi sigma r square. Okay, and you can use that
Times
value over here. Yeah,
t
times
to the
t,
power.
sorry, time t power 4. Okay, so if we have this number luminosity, we can say that this luminosity is uh, given to you because we have radius. But instead of that, if we follow the method that we have the luminosity of that star, which is equals to mean apparent luminosity, let's say it is 4 pi into, what was the value of r for that one? Sorry, r mean distance over here na. So we can use this r, we can replace this r instead of this r. Can we write the distance? It would be suitable for us.
Yeah.
Okay, let me uh, explain you with diagram. Here are we, and our here is over star, that is, I mean, this was Eta Cassiopeia, right? And we are over here at this much distance. So as we move away, its luminosity decrease. I mean, its brightness decreases with inverse square law. Actually, this is that constant. How does its luminosity are that actually this is its radiant flux intensity. Radiant flux intensity. You know, radiant flux intensity is equal to 4 pi d square. Okay, so this is what
Yeah.
its radiant flux intensity decreases by a factor of 4. I mean, decreases by a factor of square root of d. So I can say that what will be its luminosity uh, at this much distance. What is its luminosity? If it's radiant flux, it is its apparent brightness. What do we call it? It's apparent brightness. If its apparent brightness for A is, what was its apparent brightness? 1.1. Okay, let me make L a subject. If I'm going to make L a subject, L is equals to 4 pi d square into F. So just put the values, please. 4 pi, distance is 1.8 into 10 raised power 17 meter. Okay, and what is its apparent brightness? It was 1.1 into 10 raised power minus 9, isn't it?
Yes, sir.
Yeah, do it please. Calculate the luminosity, and then I will tell you how to make it uh, in terms of मावा टूरी उतना होता है 10:30 बजे है मैं मैदान लगने से मैं मैदान लगने से मैं 1:30 बजे तक पहुंच सकता हूँ खाना yes
Yeah, so covering. 17, 21 times 10 to the power
are you tired
minus 9.
a
There we go.
little bit
Wow. Okay, just a little bit. That's fine. Okay. Two. Oh, wow, this is a very big number. Two, 1, 2, 3,
eng
4, 5, 6, 7, 8, 9. 2.5 times 10 to the power minus 9.
-9 it
Sorry,
should not be
9, 9,
-9
9,
yeah
9.
because it is yeah it is power is 9 so this is the luminosity of that uh, eta cassiopeia. Actually, we have the luminosity of sun is 10 power 3.8 into 10 to the power 26 watt. So luminosity power is luminosity unit is watt. So we can say that its luminosity is equals to 2.5 into 10 power 9 divided by uh, oh yes, I made a mistake over here. Oh my god, because my number is decreasing. You have to redo that calculation, man. Sorry for that. Sorry for that.
Oh,
It is square because it cannot be less brighter than over sun. That was the problem because this was very the luminosity of the apparent luminosity of the sun, which is over here. It is
yeah,
almost 13400 watt. So almost sun appears over here just like uh, a 1300 watt bulb for us.
yeah. Uh, it is 4.5 times 10 to the power 26.
Oh yes, 4.5 into 10 raised power 36.
26, 20.
26. Okay, sorry. Yeah. So now it would be almost in the range of this Cassiopeia. So what will be the number?
Second. 1.18, so 1.2.
Ah, yeah, exactly 1.2. So we can say that its luminosity is equals to 1.2 times luminosity of the earth, the luminosity of the sun. You know what I did in this, in the last column? Did you get that or
Which
not?
one? Which one? The
In
last
the
one?
last,
Yeah, yeah. Because you're
okay,
trying to make it
because
into the terms of L, not right?
yeah, in terms of luminosity of the sun, that's why. So this is luminosity of the sun. So I just divided it with this number. एक question boy को रहा है. Okay, so should we move to the next part? See, this is HR diagram is shown in the figure. This is luminosity and the temperature given to you, and it is asked on HR diagram draw the present position of Eta Cassiopeia. So Eta Cassiopeia was having how much temperature and how much luminosity? Its temperature was 600 Kelvin, 6000 Kelvin over
6,000,
here.
yeah.
Yeah, and its luminosity is 1.2. So 1.2 is above this point. Is it? Almost a
Yeah,
little bit above this point. So I can say that, let's say this is your point, this is your position from here, this is your position from here. Yes, so exactly you can say we have to mark this position. So you can mark this position anywhere, this position. It is it is 1.2 L naught and its temperature is 6,000 Kelvin. Got it?
yeah.
Good. So very good. ये इनको बाजरा दो अली, चिड़ियों को बाजरा दो. Okay, now next one is state the star type of Eta Cassiopeia A. So what type of star that is?
Red giant, say.
Okay.
Because it's part of the main sequence and it's towards the
Yeah, it is
red giant.
almost, because it is a big star. It seems that because its temperature is almost 6,000 Kelvin. It is, its temperature is um, closer to the temperature of the sun, because the temperature of the sun is 58,000 Kelvin, and it is generating a yellow light actually. So it is in the main sequence, you can say, right?
Yeah,
Or uh, yeah, it is almost in the main sequence.
yeah,
Or you can, yeah, use that it is almost at the stage of red giant. Okay, should we move to the next?
yes, sure, sir.
Oh my god, again ratio goes. Hmm. So in this one, it is said calculate the mass of the echo Eta Cassiopeia A and mass of the sun. So we have to find the ratio. So the masses
The
are,
masses.
where are the masses? What information can be used over here? Wait. Do you have any equation in your data booklet which can be used over here?
Uh, Wait, luminosity is proportional to m to the power of 3.5.
Oh yes, luminosity is equals to or proportional to, I can write k times m power
Uh, m power 3.5.
3.5. Oh, good. So we can have the luminosity of two stars. For example, if we are going to find the mass of the Cassiopeia A, so we can make this uh, as a main equation, that L of uh, A divided by L of sun is equals to L of sun is basically L naught. So K would be cut down. So mass of Cassiopeia A divided by mass of the sun, I mean mass of the sun whole power 3.5. Okay. So if I
Yeah.
want to find the mass ratio, I would take 3.5 cube on the other side. So luminosity of A divided by luminosity of the sun whole power 1.1 divided by 3.5. So what is luminosity of that A? It was 1.2 times L naught, and its luminosity was 1 L naught. So it is 1 divided by 3.5.
Yeah. 3.5.
You are getting it? So it would be
Yeah.
gone. Your data, your answer will be
1.2 times 1 to the power 1 to the power of 1.2 to the power of 1 over 35.
yeah 1.2 whole power 1 by 1.35. Yes,
Yeah. 1
Pani will
point
not you.
1.05.
1.5. Okay.
1.05.
Oh, sorry. 1.05. Good. Right. Is it clear to you?
Yeah.
Okay. Good. So this was the equation which what we have to remember that that luminosity has a relation with mass as well. It is 3.5 times power of 3.5. Okay. Now deduce the evolutionary state of the Eta Cassiopeia A. So, what would be the final stage of that Eta Cassiopeia? So, because its mass is actually mass of the star divided by mass of the sun it is equals to 1.05. Is it? So that
Yes.
gives us a relation that it is the mass of the Cassiopeia is almost equals to mass of the sun, right? So due to that, its end would be same as the end of the sun. So what is the end of the sun?
M.
Yeah,
So
its final
1.5.
its final stage is actually what? Its final stage is same as final stage of sun,
Yeah.
which is white dwarf, isn't it? Na? The final stage of the sun is in the man sequence. It is white dwarf.
Okay.
Or you can say its remnants would be in terms of black dwarf, but it would not be a black hole or a neutron star. Remember this thing, because okay, are you getting it?
Yes, sir.
Because it is not 1.8, because when the stars are of mass 8 times the star of the sun, then sorry, star of the sorry, when the mass of, if its mass would be 8 times or bigger than 8, then its final stage would be either a neutron star or black hole. Okay,
Okay.
are you getting it?
Yes.
Yes.
I have this light buttons.
Yeah. Yeah. Question number 16. Now, question number 16 is related to your line spectra. Yeah. To somehow expansion of universe or Hubble's laws and all that stuff. So here, outline how the spectra of the distant galaxies are used to confirm the hypothesis about the expansion of the universe. So, you know, according to Doppler shift or according to Doppler's law, what do we feel or what do we have when a star is moving away from us? What about the line spectra coming to us? The line
The
spectra will
spectrum.
be red shifted,
Yeah.
isn't it? Line
Yes.
spectra will be red shifted. Red shift means its wavelength, mean the lines which are coming to us, their wavelength would be shifted towards, or the line number will be shifted towards red, will be red shifted. So simply we call it red shift. Okay.
Okay, sir.
Yes. So after that, we have this: a light from the hydrogen source in the laboratory of the Earth contains a spectral line of the wavelength 1.122 122 nanometer. The light coming from the same spectral line reaching to the Earth in the distant galaxies has a wavelength of this. Determine the ratio of the pres- present size of the universe to the size of the universe when the light was emitted from the galaxy. So actually, this question is related to your mean redshift or Doppler shift. So do you remember how do we use that Doppler shift? There are two concepts of Doppler shift. One is with speed, that v divided by c was equals to change in the wavelength divided by wavelength. It was almost equal to that. And the second thing, you remember that v is directly proportional to v is, I mean, if I use Hubble's law, v is directly proportional to d, or v is equal to sd, is it?
Yeah.
Yes, so because here we are asked about the size of the universe, so I mean, the distance, determine the ratio of the present size of the universe to the size of the universe when it was formed up. So we can use this concept of, you know, if we say that v, oh sorry, I have changed the color. V divided by c is equals to how much wavelength has been changed? फातिमा को देख के आओ यार क्या हुआ उसको.
Uh,
392
392 minus 122.
minus 122 nanometer. So it is 10 power minus 9. You can write, right? So there is another game. No need to write nano, because in the bottom one you will also write the nanometer. This wavelength is which is basically coming from the Earth, from laboratory. So it is 122 nanometer would be there. So nano and nano will be gone. So what will be your final answer?
2 minus 122. 2.2. Oh,
2.2. Okay,
yeah.
it means that if I use the Hubble's law, I can say that v divided by c is equals to radius or size of the universe when it is expanding, and this is the size of the universe, this is the size after expansion, and this is size, original size, you can write in this way. So that ratio is 2.2. So the size of the universe when it expanded, it is 2.2 times the size of the universe which was basically over there. So it is the same. Okay,
Okay.
right? So there is another equation for that one. Hubble's law is basically used in this way. So it is almost same, right? So r of the expanded universe divided by r of the original size, it is almost 2.2, you can say. Is
Yes.
there any other equation which is in your data booklet which deals with size and Doppler shift? Because I remember this one, that's why I'm using this one. So is there any other one that deals with size and Doppler shift? Actually, I do not have the data booklet with me in soft or hard copy right now. I'm sitting on my top roof and just enjoying the class with you. Yes, do you have it?
For the redshift, I have.
No. Is there any equation which deals redshift with redshift with size?
The V equals to delta lambda upon delta naught, and then there's also z
Yeah,
equals
lambda
to,
naught.
yeah, and then there's also z equals to r divided by r naught minus 1.
Oh, yes, this one will be used over there. Exactly. Oh, sorry. This would be used because this ratio would not be exactly the same one, because that Doppler shift is basically equals to this one. That equation will be used. Well, I was searching for that equation, but I did not remember that. Yeah, where is that equation? So let me redo this question for you. This question will be done in two steps. One step is, in step number one, you will use that v divided by c is equals to delta lambda divided by lambda naught or lambda, which is your Doppler shift, right? Which we found that it was 3.392 minus 122 divided by 122, and that was equals to, it means your z was equals to 1 point, you told
1.2.
me 1.2. Yes. Then we knew that z is equals to r divided by, what was the equation? R divided by r naught minus 1.
Yeah, minus 1.
Yes.
Yep.
From here, r divided by r naught is equals to z plus 1. So your ratio is r divided by r naught is z is your 1.2.
Plus 1, which
Is
is
it
2 point.
1.2?
Yeah, 1.2.
Okay.
Wait, sorry, 2.2.
2.2, yes, it is 2.2. So it was 2.2 plus 1. So you will get 3.2.
3.2.
The ratio of expansion divided by original size is 3.2. So now the universe has been expanded to, I mean, that galaxy has moved 3.2 times away from the size of the original one. Okay? Is it clear
Okay.
to you?
Yep.
Okay. Yes. The last two parts of the uh, question was evident from the Planck's space observatory suggests that the density of the matter in the universe is about 32% of the critical density of the universe. State what is mean by your critical density, right? So critical density was basically that density of the earth at the, when the earth would be, or it would be just straight plane, right?
Yes, sir.
So we can simply say that critical density is the density of any material or earth or universe, or you can say it is a density of matter, the density of matter in the universe. So it is the density of matter when expansion will become linear, or universe would have universe will have no, in simple word you can say that it will have no curve, or it would be plane, or it would be plane, or it would be flat, or whatever you call it, it would be its critical density, right? So calculate the density of the matter the in the universe using Hubble's constant. This 70 megapars. Hi, 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 hi. It makes your brain tiring. These all calculations.
Yeah.
Okay. So here, which equation will be used over here from your data booklet? Which equation would be there for that deals with uh, this Hubble's constant and over mm, density of the Earth? Okay. Do you have an equation nearby to
No,
you?
sir. No, sir.
Yes. No, any equation which is stating Hubble's law. State the equations from Hubble's law, then I will let you know which equation will be used. Any equation in which Hubble's is used. No one? Yes, Abdullah?
Z Z equals to H
Z
not
equals
E
to H naught into
D.
D. Okay, good. So that was basically one of the equation. Okay, what else?
Then there is T is estimate of 1 upon H naught.
Okay. Anyone else? Anything else?
Uh, no.
Okay. So it will be probably we have mass and all that stuff. Okay, if I just do this part later on for you, because when I will remember some equation, that which equation will be linked over here, then I will be able to solve that. Okay.
Yeah.
Okay, so if we just stop it over here, because I think my processor has stuck now. Really. So
Yeah.
we will solve remaining questions. uh, this question number 17. If you solve that question, if you try that question, and if you have some problem, we will discuss. Otherwise, I will solve it for you. Right?
Okay. Yeah, sure.
Okay. Yeah. Inshallah, tomorrow we have a class, and if you will be available early in the morning, I will appreciate that. Early in the
Yeah.
morning mean my early in the morning. According to your time, we are 3 hours behind you.
Tomorrow, I think in the morning I'll have maths, and then I have
Okay.
chemistry after that. I think the evening time is much nicer. But then Ramadan we can